So welcome to the third video of exploration in DeepRL, and in this video we will be talking about memory-based exploration. So that's our agenda so far. So in the exploration with DeepRL lecture, we started with count-based exploration. In the last video we talked about prediction-based exploration, and in this video we will talk about memory-based exploration, where we actually cover methods that implement some form of memory to store past transitional and experiences. Why would we actually want to do this? So we have seen that a reward-based exploration works well in many applications. However, we also have seen in the last two videos that it still suffers from several disadvantages. One disadvantage is that function approximation in general is slow. So if we have seen in the prediction models, we usually use some kind of function approximator that we use as a prediction target to actually maybe learn the dynamics of the system. However, those function approximation is usually slow in terms of approximating values which are trained on. A second thing that we did not really explicitly cover in the lecture so far is that the exploration bonus is a non-stationary target. So we actually add the intrinsic reward to our reward signal that we provide to the agent, and this intrinsic reward is actually not only there's not only a stochastic component which is actually part of the extrinsic reward, but it also if states are no longer novel anymore, the agent will see the same transition and gets different reward in the end, and this means actually that it's a non-stationary target. And from that also follows something called knowledge fading. So states are no longer novel in time and do no longer provide intrinsic reward signals. And this is actually also the idea of that actually addresses memory-based exploration. And the idea of memory-based exploration is to use external memories in combination to resolve such disadvantages as laid out before. Okay, so actually let's start where we actually ended in the last video. So in the last video we actually introduced R&D, so the random networks that actually had a prediction target that's not the dynamics of the system. And we have seen in the paper in the end that R&D in general works great, but it suffers from the episodic setting, which was actually just solved by the authors by omitting the truncating of the rewards and just letting the reward go over the episode, the end of the episode, which was also actually mentioned by the authors in their paper. So in order to actually solve for this problem, there is a simple idea, and the simple idea just says, okay, let's use two modules. By the way, this is actually a follow-up paper on based on R&D, which is called Never Give Up, so NGU, and this is actually proposing the solution. So the idea is actually to use two modules. The first module is the R&D module. It's something like a lifelong novelty module, which is actually implemented as it was introduced originally in the publication. However, there is actually a second module that is used in combination with the R&D module, and this module is actually responsible for implementing something like an episodic novelty module that actually allows for a rapid in-episode adaptation. So actually R&D is actually something that runs across episodes, like for a lifelong, like from the training course over the agent's lifetime, and the episodic module is actually only considering the current episode and this setting. Okay, maybe let's show a little bit the diagram of this algorithm. So what you see in here, it's the standard setting. You have an embedding network and you have a forward model and all this stuff. And here's actually what NGU is proposing. So you have on the top the lifelong novelty module, which is actually the R&D random network. Here you have the prediction network and the random network, and you train those networks to come close to each other, and then getting you some value alpha t. And on the bottom line, you have the episodic novelty module. And this is actually the new thing, and I will actually explain all the components in the upcoming slides. So what's actually happening is the lifelong novelty module is something that runs across multiple episodes, and the episodic novelty module actually consists of something like the intrinsic curiosity module in here, which actually gives us a state encoding. And this state encoding in the episodic novelty module is actually put into something called an episodic memory. And this episodic memory is used to actually derive how novel a certain state within an episode actually is. And from this episodic novelty module, we get a short-term per episode reward that's actually active from within one episode. Okay, so the R&D actually is just there to derive a lifelong novelty bonus. The exploration bonus is given through this formula. It's just like the usual R&D bonus with an offset. And what we actually do is we just normalize or standardize the novelty bonus by a running mean and a standard deviation over a time window. So this is just what we're doing, and this means we just keep a window over the last R&D errors actually, and we standardize the reward. The second module, so the episodic module, is actually a little bit different. So through the ICM, we actually get the encoding of the state, and what we actually do, or what's the general idea is, actually to put all the states that we've seen in the episode into an episodic memory. And if we then actually get a new state, we just compare the encoding of the current state with the content in the episodic memory. There's a bunch of different metric functions that you can actually use. This is the one proposed in the paper. It's just like the extrinsic reward at this point is just 1 over and then the square root, where actually k is some kernel function. I think they used this, the Euclidean distance in this case. And the number of nearest neighbors nk, so we run a k nearest neighbor on that. So we just use something like the top 10% of nearest neighbors in the memory. But there's actually also a bunch of different functions that you can actually use. You can actually use them or consider them as a hyperparameter, and just a constant c actually in here to avoid a zero sum. So yeah, originally the paper proposes to use the kernel function like this, where d is just, it is the Euclidean distance in this case between two samples, and then you have a squared Euclidean distance of the k's nearest neighbor to be more robust, and some small constant epsilon. So this is actually how you derive the extrinsic reward from the episodic novelty model, and what you then do is actually you just combine those two. And they combine it like this, that they actually provide the intrinsic reward as a multiplication between the extrinsic reward provided by the episodic novelty module plus some clipped version of the R&D output reward from the R&D, where L is something considered like a reward scalar from the R&D module. And the general idea, or what NGU actually wants, is NGU tries to enforce that we do not revisit the same state within the same episode, because actually then there would be a high similarity with samples from the episodic memory, and we also try not to revisit the states that we also have seen in previous episodes, which is something that's actually introduced using the R&D module that's actually capable of doing the lifelong learning stuff. Yeah, so actually here you can actually somehow counteract the limitation of the R&D, where you actually have to truncate the rewards at the end of the episode, and then you can actually run it like it was supposed to run, and you can run the agent in the environment as it is defined. There was also some follow-up work on top of that. The follow-up work is called Agent 57. So Agent 57 is from a paper from last year. It's actually the first RL agent that consistently beats the Atari 57 suite. This is also because why it is called Agent 57, which is actually the 57 games of the Atari suite, where they actually also provided a human benchmark from that. And the basic idea, so there's also a nice visualization of that actually shows the kind of improvements that actually have led to Agent 57 in the end. So they actually started with DQN and all the improvements over DQN. then components such as RNNs and long short-term memories, then everything that we have learned in exploration, all that ideas, you will see like curiosity in here or R&D in here. You see the ideas of episodic memory that we actually introduced to NGU in the upcoming slides, and then on top of that they used further ideas to actually compile it into Agent57. And it boils actually down to two main improvements over Never Give Up. And the first one is actually that instead of just using one policy, we maintain a population of policies. And with these populations, we have actually a set of parameters that are actually configuring the policies. So each policy actually has an own pair of exploration parameters, beta and gamma. So you have n policies and you have parameters from them, and they are configured to be like this. So the policies with a high beta value and in turn with a lower gamma value, they should make more progress at early stages. So they actually should be more explorative in the beginning. And policies with a high gamma and hence a lower beta actually are there to make more progress at later stages. So really exploiting the knowledge from the environment and really running like greedy updates to actually improve the value function. And what they actually also do is they put on top a meter controller that actually implemented as a sliding window upper confidence bound agent that actually is trained to select from the population of policies in order to actually select the actions that we actually take. And the second idea, actually, besides of these, that we have a population of policies, is actually that we reparameterize the Q function. So what they actually do is now what we did in the beginning is that we actually added the intrinsic reward as a kind of bonus onto the extrinsic reward and just provide a single reward to the agent. The idea of Agent57 is actually to decompose these two components, and what this actually means is that the Q function is actually composed into the intrinsic and the extrinsic. So this is the intrinsic and the extrinsic influence, and we have the parameter beta that actually weighs the intrinsic influence. And what they do is actually during training, they actually train both parameter sets, so theta extrinsic and theta intrinsic, separately. So they train those networks separately, also with the rewards respectively. And this is actually allowing them to just trade off between those different population and parameters, and to actually implement the meter controller that actually steers gamma and beta at this case. So with that, they actually outperform all the other algorithms actually on the Atari 57 benchmark. If you are curious about this kind of work, it's a very nice paper that you can also read. It's not much theory embedded, and it's easy to follow along. Just grab out this paper. It's available on arXiv, and then you can actually read through it. Okay. However, in the past few papers, you also have seen that that we actually used as a kind of a distance measure between two states. We just refrain to the Euclidean distance between two states. And it turns out that it's actually not always a good idea to just use the Euclidean distance between two frames, because it's not really a well-defined metric to give you a distance between two states. And this is actually the idea that's counteracted in the episodic curiosity module introduced by Savinov et al. And the general idea is actually to measure, as a distance metric between two states, to measure the number of steps that the agent actually need to take in order to transit from one state to another. So the number of actions that you need to execute in order to reach a state from another state. And this actually defines the distance the distance metric on the state space. And if we have a well-defined metric for that, the novelty then just depends on some kind of the reachability between those states. So if we have a state and we have 2 or 3 states that are really like reachable within one time step, those states are not that different from each other. However, if there is 2 states and they actually look a little bit similar, but I have to take like 20, 30 steps in order to reach the state from the current state onwards, then the distance is really large. So, and this is actually what they actually try to capture with the episodic curiosity module. What's the general idea? So as what we also did in the beginning, so actually what we're doing is we just clear the episodic memory on an environment reset. This is something that I didn't say in the beginning, but I think it was somehow clear that the episodic memory is resetted when we actually start the episode again. And then at each time step t until the episode ends, we actually do the following. First, we compare the state st with all the states we already have in memory. So then, if it takes more than k steps to reach state, then the agent, so from the current elements in the memory, if it takes more than k steps to reach the state st, then the agent gets a bonus. And if the bonus is large enough, then we add st to the reachability memory. So this is actually how it works. And the question now is, I mean, this is like a high-level discussion of this algorithm, but there is one thing that we still need to learn, and this is just how can we estimate the reachability between two states. So in order to just having already some states in the memory and we just see a memory, how can we actually estimate how many steps k we need to reach a state from the states that we already have in memory? So that's a question, how can we actually do this? And this is actually what they proposed in their paper. So in the ideal case, we would have something like this. We would have something like a transition graph that actually tells us that we can actually follow through and that we can actually traverse, where we can actually say, okay, it just took us like 5 or 6 steps. However, in practice, it's not really possible to build that up because we have restricted memory. So we have limited memory, we cannot store everything. And even if we could store it, like it's really hard to build such a transition graph because we also have like stochasticity in the environment and everything like this. So the solution, or what the authors actually propose, is to train a Siamese neural network that predicts actually how far two states are apart. So Siamese network is actually a metric learning method that actually learns a metric on a certain space. And this is actually what we want to do. We want to have a distance metric that is actually trained using the data we provide. And how does it work? Actually, episodic curiosity builds on top of two networks. The one network is an embedding network. The job of the embedding network is just to encode states to feature vectors, because actually we have high dimensional states. We cannot just store them. We cannot directly work on high dimensional states. We need to encode them into feature vectors. This is like what we did all the time already. So we just reduce them to a set of features that are describing the state. And then we have a comparator network, Z, actually that takes as input to feature vectors and actually outputs a number between 0 and 1, which is actually something like a reachability score or probability that says that within k steps, k is to be defined. If it's 0, then it's non-reachable. So these two states cannot be reached from each other within k steps. And if it's 1, we say, okay, it is reachable within k steps. Based on that, we actually train an R network, which is a reachability network, simply as a classifier trained on a logistic regression loss based on the data from the trajectory and the two networks in here. And we just train it to output to actually say, is it reachable within k steps or not? And then we can actually say for a certain set of states, actually where we have a reachability within k steps and where we have non-reachability within k steps. And this can actually just train using a logistic regression loss on the data we just have. Okay, so if we all put this, if we put all this together, we can also formulate a simple algorithm out of this. So at every time step, we just take an image or an observation and process this observation with the embedding network, from which follows an embedding vector. So the embedding vector is just called E, which is just a function over the encoder over the observation data. Then we compare E with all the embeddings in the buffer that we already have. So we have the embedding and we compare it with all the elements from the buffer with our comparator network C. And from this, we get actually for all the elements, we get actually a list of compared values between 0 and 1, from which we can fill the reachability buffer in here. And now what we can do from there onwards is actually we can compute a similarity score between the embedding E, so between the current state, and all the elements in the memory buffer. And we can use this as a function, and this function is something like a hyperparameter. It could be like a max function. So actually, I would say in this case, I would say the similarity of the current observation is the maximum similarity from all the states that I have in memory, which would be theoretically a good choice. However, it's prone to outliers. And what the paper actually proposes is to use something like a 90% percentile that actually gives you the similarity score of that image as an indicator of novelty for the current state. And if we have this, so actually we have this similarity score, we can then compute the curiosity bonus as simply using our bonus function, and they use something like this, where we actually have two values, alpha and beta, where alpha is simply a hyperparameter that tunes the scale of the task rewards, and beta is just defining the sum of the reward. In their experiments, 0.5 works very well for fixed duration episodes. However, they make a study on that too, and you can look this up in the paper. However, it's not making any main difference for the understanding of this method. Okay, so reachability is a nice thing that we can actually do, and this is actually outperforming things like Euclidean distance between two states. It's like a well-defined metric to define similarity between two states. Depending on this, if we talk about similarity and reachability, there's also another idea that we can actually do exploration, and this has been proposed in 2020 by Ecofed et al., which is called Go Explore. And the motivation of Go Explore is actually that there's actually problems stemming from the sparse reward setting and the intrinsic motivations. And it's a very nice work because it actually describes problems that you might have thought about, but it's not really addressed and formulated that well enough in previous work. So if we're talking about intrinsic rewards and sparse intrinsic motivation and sparse rewards, we actually can line out two main problematic situations. And the first one is actually the problem of detachment. So the problem is that intrinsic rewards are actually always a consumable resource. So actually we have an intrinsic reward that's somehow defined on some kind of novelty over states. However, if we have seen those states, these intrinsic rewards will actually be invisible and they will get lost. So they actually go away. So a short-term focus hence lies in such areas, but with time, such area just becomes less interesting to the agent. While this is not in general a problem, just remember that as we're using also neural networks all the time, we also have the problem of catastrophic forgetting, which means that we forget things that happens to be far in the past, and if we do not continuously see them, gradient descent updates on a neural network, we actually tend to lose information from that samples. And the second is the problem of derailment. And this actually describes the problem of revisiting an interesting state again in order to further explore from there. And they actually make up a very nice example to do this. So imagine that we have something like this two-folded maze, and we can either go left or right. And what you see actually is the intrinsic reward as it is actually assigned to the environment. It's just distributed over the environment, and as we have seen, if we have seen no state until now, every state gets equal novelty bonus. And now if the intrinsically motivated agent starts exploring, just imagine that the purple area is just the agent going through the maze. It starts exploring, and it will get it will actually collect the intrinsic reward. And just imagine that at this point actually the agent dies or something happens, so the episode ends in this case. What would then happen? So in that case actually, if the agent starts again here, there might be a high chance, depending also on your hyperparameters, that the agent will go on that side. because actually there is maybe, depending on the extrinsic rewards, in this case is not that much, it will go this side. And the problem is that actually there's a lot of intrinsic reward that's still in there. However, the agent just fails to discover it because it is somehow detached from it, because it already collected all the intrinsic reward on the way to that area. So this means that we have some detachment because the intrinsic reward, so these states are all not anymore novel to the agent, so it has no incentive to actually visit those states. So the problem is, in order to actually reach such states where we can actually go on exploring those highly novel states where we get more intrinsic reward, is actually how previous work actually did it. They just run the policy again with some stochastic perturbation in a hope to just reach the desired state again. However, as you might also expect, with a naive perturbation in a complex environment, this is really unlikely, because actually, if we have some randomness also already in the environment reset at the beginning, we would need to, because we actually, in order to reach such a state, this might actually require to take really precise action to go there again. And if the environment is not deterministic, it's like the chances are almost zero to actually go to that state again with the same action sequence. So how the authors actually try to achieve this? So actually in their paper they actually address the problem of detachment and derailment and what they actually do is they propose an algorithm that consists of two phases. The first phase is called explore until solved, and the second phase is called robustify. However, they define it to be optional for the setting of the algorithm. So the first thing to mention, they call state or observations actually cells. And what you see here is a screenshot of Montezuma's Revenge. And what they do is they just take the observation and scale it down to a 11 times 8 pixel image, with each pixel having an intensity of 8 different values. So it's a 3-bit representation. And they then run actually the first step, which is called explore until solved. So in this step, actually, there's no machine learning involved and no neural networks involved in here. It's just a random or semi-guided exploration of the agent in the environment. And the main goal of the agent is actually to find interesting cells. What defines an interesting cell? It means that it's a newly discovered cell, or it's also a cell that actually has a high reward obtained in order to reach the state. So the entire trajectory sequence, if this entire trajectory sequence has a high reward, then it's also an interesting cell. It's not only the novelty of the cell itself. What do they actually, and how can they actually do this? What they need for this? For each interesting cell, so they maintain a list of interesting cells, they actually store the full trajectory, the sequence of observations and cells to get there. They actually store a snapshot of the environment state or the simulator state, the total reward of the trajectory they actually obtained, and the length of the trajectory. And if they actually revisit a state during the exploration, they update the entry if it is better or not. So if it has been a shorter trajectory or if we got a higher reward, this actually leads to an update of this data from that interesting cell. And what they actually compose it within explore until solve, they have two ideas, and it's called go and explore, because this is also why the algorithm is called like this. And they actually work in iteration to each other. In the first step, so go, we just use a heuristic to choose a good cell and try to go there. So we have a list or an archive of such interesting cells, and we then use a heuristic to actually go to actually select such a cell, like the best reward, or it has been least visited, or something else, and we just choose this cell. And what we then do is we just activate this cell, so we use the snapshot of the environment state, we are in the cell, and from there on we keep on exploring using random actions from there on. So no policy, no network involved. This is the first step. So this is the idea this is actually the idea of the algorithm. However, also the the authors by themselves lined out that there's a limitation of the first phase. And to go to a cell is only easy in deterministic environments because they actually made a very huge assumption. And the assumption is that the environment is deterministic. In order to go to a cell from an archive, we need to be able to reset the environment, and we need to be sure that the series of actions that we actually took and that are stored in the archive, they actually lead to the desired goal cell. And this is easy to achieve in something like a computer game, in Atari, especially in there, because there the same actions will always lead to the same result. So you can actually you can actually select the action, and you will actually reach this cell. But however, as we actually also want to use RL in real world settings, and real world settings are hardly deterministic in general, so that's a clear limitation of that. This is actually why we need the second phase. We want to make the trajectory to the good outcome cells that we found through the random exploration more robust to noise and non-determinism. So that's actually the idea of the second phase in order to reach such a state. And from there on, they define an algorithm that's called the backward algorithm. And in order to understand this algorithm, consider a sequence C1 until Cn, where Cn is the goal cell. So it's like the cells along the way, and Cn is the goal cell that we want to reach. And they propose an algorithm like this. So we just initialize Ci as Cn minus 1, so it's the state before the goal cell. And what we then do is we set the environment to the snapshot of Ci, which we actually stored in the memory, and then we train the agent to reach Cn. So we train a policy that actually takes us from Ci to Cn. And when you find a trajectory that actually has a higher or an equal reward, we go one step further. We go one step back in the episode, so to Cn minus 2, and we will then go on with step 2 and try to reach the goal state from that state onwards. And then we stop actually when we are at the beginning of the episode. So actually this actually helps to train a policy to reach the goal state in non-deterministic environments. However, now what's now in turn the problem if we have non-deterministic environments such as Atari? We would need to introduce non-determinism in Atari, and this is actually if you have played around with it, you see that there is like things like no ops, where the agent is not even allowed to take an action every time step, but the interface just implements a no-op operation in this case, or something like sticky actions, where actually the agent selects to take an action, and this action is actually selected more than once actually by some probability that's provided by the simulator. So this is how you can actually introduce non-determinism in deterministic settings, in this case such as Atari. So if you do it like this, and also in comparison to what we have seen in the lecture so far in the exploration, you see actually the progress of Montezuma's revenge if you use Go Explore versus what we have seen before. And you see that here the R&D module did a very decent job until this point. However, Go Explore actually solves the problem of detachment and derailment, and actually outperforms all the things like in this case finding all the rooms that they are to find in the environment, because we get actually never detached from the intrinsic reward. Building on top of Go Explorer, there's actually two works that actually try to make Go Explorer more applicable in practice. The first one is the algorithm it's really called like this: first return, then explore, and it's actually a version it's like a policy-based Go Explore improvement. And the thing is that in Go Explore we actually needed to reset the simulator, and so instead of resetting the simulator and initializing it with a state, what we want to do is we want to learn a goal condition policy that is actually trained explicitly to reach a state. So we actually we have the trajectory that actually led us to reach a state, and we through the backward algorithm we actually initialized our simulator and tried to reach it. However, what they propose is actually, instead of setting the simulator or resetting the simulator all the time, we learn a goal condition policy that actually learns to reach a certain state from another state. And as we already have some initial explored trajectory that takes us somewhere to that state, what they actually try, or what they actually suggest to do, is something like mainly follow the best trajectory that has been found so far, and do something like self-imitation learning to extract more information from the successful trajectories that we observed during training. So a second idea in this case is actually, so this is actually something like a diagram over first return then explore, where you have the phase on below. This is actually what the extension stems into, where you have actually the robustification phase, where you have a policy, and the policy is trained from demonstrations and tries using imitation learning to actually get a policy that is robust to stochasticity and actually is able to reach a target state. So this is actually the goal condition policy that we're learning on the bottom in here. And there's also a second work, it's called memory-based trajectory conditioned policies for learning from sparse rewards, which is really like very similar. It's really like policy-based go explore and above. However, what they do is like they maintain a memory of demonstrations collected during training, and they use more the self-imitation learning. In this case, they didn't use the self-imitation learning, just and they actually, what they do is actually they prioritize trajectories that end with rare states during sampling. That's also a difference from them. However, both of these papers are really, really similar in practice. So they actually build on the same idea and have the same motivation. Okay, so this is memory-based exploration. It was some very recent work. I think it's like from this year. Let's make maybe a little summary of what we have learned in the exploration strategies lecture. I think if we recap the last two lectures, actually we studied different families of algorithms and settings in this case. So we started with multi-armed bandits and their theoretical assumptions. So we had really like a mathematical formalism to study the regret of these algorithms and really to have something like a lower bound where we actually can do exploration at its best. Then we actually motivated the challenges that are arising from going from small MDPs to high dimensional, also POMDPs in this case. And actually we found different families of methods that we can use to guide exploration in DeepRL. We have found count-based exploration, where we tried to do the count-based thing that we have seen in the first lecture and to approximate it using density functions or models or neural networks. Then we had the prediction-based exploration, where we could actually predict a dynamics model, or we have seen random networks in this case. And in this lecture we talked about memory-based exploration, where we also maintained something like a memory of states that have been visited in order to more properly estimate the novelty of a state. So summarizing, we can say exploration is a really hot topic in current RL research. So in the recent conferences, you will see a lot of papers that actually try to do exploration better, because exploration is really one of those things where RL is merging towards. And always like it's not only about DeepRL in this setting, so there's also a lot of work that tries to prove theoretical assumptions and bounds for bandits or for contextual bandits on small MDPs, but of course you will also see a lot of work that does exploration in DeepRL. So this is the references that we used to compile this lecture series. If you're interested, you can, I really encourage you to also look this up. However, you can these are especially the first source is like a really nice lineup where you can see all the relevant and most recent work on exploration.